So our next speaker is Yaov Artzi. Yaov is a associate professor in the Department of Computer Science at Cornell University. He serves as the associate faculty director of Archive and is a researcher at ASAP. His work explores natural language acquisition, modeling, and use from a computational perspective, with a particular focus on automated situated systems. His group's work is anchored in natural language processing and machine learning, and frequently extends into robotics, computer vision, and cognitive science. His contributions have been recognized with the NSF Career Award, multiple paper awards, and a recent Tackle Test of Time Award. He is also one of the main organizers of COLM, which will be in Montreal. And I must say, as an area chair, I think this is one of the best organized conferences I have ever reviewed for. So please welcome Yaov.
Okay, so I'm going to talk today about learning via agentive interaction. I played with the talk throughout the week, changing what I'm talking about based on what I was listening here. Originally, I was planning to talk about this paper that's coming up in COM, and I'm mentioning it because Elaine mentioned this paper about convention formation in her talk. It's an evaluation paper. Yes, we get where we are able to prompt models to do that, but largely the results are actually kind of like it's a negative results because the prompting is very task specific. It's not really getting us the general behavior that humans display. So after we did this, that was in 2024, Elon came and said, I can fix that. And I didn't believe it. But I gave him a month to do that, and then I forgot about the deadline. So it took much longer than a month, but he was able to fix it to a very significant degree. And this is in COM 2025. It's a really cool kind of like post-training methods with cooking up of like found data to get a really crisp signal and getting this very general behavior and then evaluating it like in a lab style setting that is really inspired by cognitive science. So it's a really cool paper, but I'm not going to talk about it today. So what I'm going to talk about today? So I'm going to talk about learning from implicit conversational signals, where the idea is that you can do post-training and by bootstrapping from past interaction, by retrospectively looking at them. This stuff came up just a few hours ago in some Twitter thread by Alex Demakis. It's kind of interesting, this whole idea of like continual learning. So this is what I'm going to do there. And then because throughout the last few days, something that I've noticed a lot is a lot of the kind of like behavior that we are seeing are happening in context. That's what a lot of agents are doing, especially the software agents. They try things, they see it in context, and they adjust their behavior. I'm going to talk about in-context reinforcement learning, for where you kind of like learn from rewards in context without parameter updates, and you see some interesting learning behaviors there. Okay, so I'll start with the first one. So the gist of this paper is that we can learn from conversational interactions by just kind of like looking at them and kind of like improving from these interactions and analyzing them. And the reason for that is that conversational interactions, they span multiple turns. And this creates this kind of opportunity to learn from observed behavior, because the model outputs, they're naturally followed by human response. This is this like really turn-based interaction like you have with ChatGPT. And these responses, the human responses, they're influenced by the model output and by its quality. Okay? And this kind of observed behaviors can form a really informative learning signal. And why is this cool? Well, there are two important properties of this kind of signal that are not present in the kind of signals we use nowadays for post-training. One of them is economical. It's just free. It arises naturally from our deployment, where even when you're doing human preferences nowadays, we go to annotators. And second, and this is really important, it's always on distribution. So if the models change, as the world change, this signal changes, right? So there is this really interesting opportunities for adapting, personalizing, reducing training costs, and so forth. So you can have like models that are really dynamic and change over time and keep up with the world. So how does this signal look like? Well, it's often pretty implicit. Sometimes it's explicit. And that happens because when you are in a conversation, the partners change their behavior based on the partner on what the other side is doing. So for example, speaker utterances or their behavior, following a response from the other side, from the interlocutor, they encode feedback about this response. So errors may elicit rephrasing, pivoting of the interaction, scolding, direct corrections, etc. So for example, in this example, Charlie Brown is getting and decoding feedback about how to lose, and maybe he will learn how to do it better in the future. Although if you know anything about Charlie Brown, is that it's not a good learner. On the other hand, correct responses are very different in what they entail, right? So when you get something good from a model, what are you going to do? You're going to often build on top of it. Sometimes you're going to praise the model or give it like explicit confirmation. Often you're just going to continue and move on to achieve your goal. Now, in this kind of signals, they're often implicit. So when you build on top of something, there's no explicit praise or anything. You're just moving on with what you want to do. But the point is that you can kind of like, the models can extract them by retrospectively analyzing these kind of interactions. In order to do this, we introduce an approach called respect that stands for learn retrospectively. It's a three-stage process. The first, you take the model and deploy it for conversational multi-turn interactions with users. And then you take the same model that participated in these interactions and you have it analyze these interactions in order to get feedback, a signal about its own actions. And this is a very important distinction from the more common scenario of LLM as a judge. The model is not going to analyze the quality of its own actions directly. And indeed, in our experimental setup, we build a scenario, so this is actually impossible. What the model does, it analyzes follow-up utterances from the human and tries to decode the feedback from there. Once we decoded this feedback, we can convert it to a learning signal, rewards, or some other types of learning signal. We're going to experiment with a few, and we're going to retrain the model. There was this really interesting dynamic happening in this kind of process when you think about it over time. Because the performance of the model, what kind of errors it's doing, how good it is, the task that we asked to do, is really going to influence how well it's going to decode. And what it can decode will influence the training signal, and in turn, this whole thing kind of like loops together. So it's really important to ask yourself, what's the dynamics over time? So what we do is we take this process and we deploy it iteratively in rounds, where you go through these three stages, and then you redeploy the model to interact with users and repeat this over and over again to kind of like to observe long-term trends. This is going to solve also evaluation because we take this this model and redeploy it, and in the next round, we can see if its performance is improving. Okay? Okay, so I'm going to go through each of those three stages in turn, and then we'll show the experiments and the results. Okay, so the first thing is where we deploy the policy. So we design a scenario that is really tailored for research in our lab, that to reveal kind of like the critical properties of interactions that we're interested in, while still scoping the problem. So we can keep the sample complexity and the computational needs at kind of like at the level of an academic research lab. So we introduced a scenario called multi-ref. For those of you familiar with, and Elaine mentioned these kind of scenarios, multi-ref is a generalization of reference games. There are several really important distinctions from reference games. So in reference games, the listener selects a single target. That means the action space is just the number of images they observe. Whereas in multi-ref, they select a subset of these images. So instead of having a solution space, which is the number of target, now we're going to have this very large combinatorial solution space, all possible subsets. And this is going to naturally lend itself to a gradual construction of the solution because it's a subset of items. So instead of a single turn interactions like we see in reference games, we're going to have a multi-turn interaction. So, and this is really important because this is kind of like essential for the kind of scenario that you want to study. In our deployment, the model always takes the listener role. So how does this look like? So this is kind of like an illustration of the multi-ref scenario. We have a speaker, always a human in our case, and a listener, always a model. Together, they observe a set of images. They see the labels in a shuffled order, so they need to communicate about the images themselves. The speaker gets a set of targets, and their goal is to get the listener to select these targets and only these targets. When the listener selects them, the interaction concludes successfully. If they're not able to complete it within 10 turns in our setup, then the interaction fails. So for example, if this interaction may start with the speaker saying a diamond head man without legs, and then the model, in this case, selects image I. This is probably a good selection. It's one of the targets the human specify. Indeed, when the human continues the interaction, they said another diamond head man. So they're really building on top of this solution. And you can really see the kind of like pragmatic considerations that appear in this scenario, as well as the visual language. In response to this, in this example interaction, the model selects image C. Visually, it's not a terrible mistake, but it's not one of our targets. So the human is going to try to correct it. They do it in an implied way. They don't say this is terrible or this is wrong. They say the other one with diamond head and triangle budding triangle leg. And if the model does it well, they will select deselect C and select G, and the interaction will continue until they either run out of turns and then they fail, or the listener selected the right set. Okay? So what do we have here? So we have a reference game. This is based on a reference game. So this is really a classic prototype in cognitive science. So we're really building on top of research that you can trace back to the 1960s. And it's really been it's a workhorse in cognitive science to study communication and grounding. This tells us we're going to get some really interesting interaction here. We're going to use for a visual stimuli tangrams. We use tangrams from this very large set that we created a few years ago. It's called Kilogram. So we have this diverse set with abstract shapes. There's two important things about tangrams. First of all, they're very hard and out of distribution for contemporary LLMs. State-of-the-art LLMs, you give them a tangram reference game, they will perform terribly. This is important for our experiments because it means that we have room to improve. So we can see a very significant effect if our learning works out. They also have a lot of history in cognitive science, and this tells us that we are going to get very diverse description with a lot of abstractions and visual language. And finally, because of this subset selection setup, we get this multi-turn, rich interaction with a lot of dynamics, corrections, rephrasing, pivots, all the phenomena that are going to drive the learning process. Okay, so given this kind of interactions, we're going to take the same model that performed these interactions, and we're going to retrospectively analyze these interactions to decode feedback. Okay? The underlying assumption, kind of like hypothesis, more like hypothesis here, is that the implicit conversational signal is actually expressed in a way that is relatively constrained and general. So even if the model is terrible at the task, and the model is going to be very bad at the task initially, it has the ability to decode it, because it's something that is very general about language that you acquire during pre-training. And if that is possible, we are at a position that the model can kind of like bootstrap and improve over interactions from humans completely autonomously. It doesn't require any kind of like external annotation or something like that. We take the simplest possible approach in order to decode the feedback, and we simply use prompting. We use a general, task-agnostic, and text-only prompt with a very minimal design. The fact that it's text-only is really important here, because it tells us it's impossible for the model to play the role of a judge here. It simply cannot tell if given the action and the targets, if the action is correct, they don't have access to the targets. So what do we have here? We have some instructions. We have the history, just the text. We have the model action, select C, for example. The follow-up utterances, here comes the signal that we are trying to decode. And then we ask the model in a very simple way, kind of like decode if this is in this prompt example, if it's positive, neutral, or negative. In this case, it's going to be negative. Or we're also experimenting with the binary signal, where we drop the neutral and just ask if it's positive or negative. Okay? Given this feedback, we convert it into a training signal. We experiment with 3 training algorithms. We do filtered fine-tuning, reinforcement learning, and utility maximization. And we have this color coding here. I'm going to use this color coding throughout the rest of the talk. So filtered fine-tuning, FFT, very simple. We are just going to keep all the examples with a positive feedback, discard everything else, and then we're going to maximize their likelihood. This is very similar to some kind of like very simple recipes learning with verifiers. For RL, we're also going to take a very simple approach. We're going to take the feedback and we're going to convert it deterministically into a numerical reward. And then we have a contextual bandit setting, just like RLHF. It is not going to be an online setting. It's offline. So after every round, we run an offline process. And we're going to use a reinforced style policy gradient with a gradient estimator and a hacked IPS coefficient. This is what you see here. This is kind of like to handle cases where we have a negative reward. And if you kind of like try to see what's happening here, if you have a negative reward, this gradient can explode very fast. And finally, we do the utility maximization using KTO. The feedback that we have can map directly to a kind of like a preference pairs that are unpaired. So good feedback are preferred, negative feedback are dispreferred. If we're doing ternary, we're going to discard the neutrals. And we use KTO, and we try to follow the recipe from the original KTO paper as much as possible. Okay, so this is the process. We deploy, we retrospectively decode the signals, the feedback signals we convert into training and retrain our model, and then we deploy again, and we're going to repeat it again and again and again. For experiments, we do concurrent randomized deployments with human users, and we're going to vary the feedback decoding, so binary versus ternary, and we're going to vary the training methods. This gives us 6 systems that we are going to deploy for 3 rounds. Then we're going to pick the winner, and we're going to deploy it for another 3 rounds because we want to see more long-term trends while still controlling our costs. We evaluate task success and utterance accuracy, and for utterance accuracy, we're going to have some manual annotation because for task success, we can just look at like how well the interaction has succeeded. We use EDAFIX28B. EDAFIX2 was the state-of-the-art models when we did these experiments for multimodal. Okay, so this is the main results. So what we're seeing here, we're seeing the 6 system here at the top. B and T stand for binary and ternary feedback signal. This is filtered fine-tuning, reinforcement learning, and KTO. We also have additional 2 curves here. This one is a concurrently deployed human-human interactions. So given 10 turns, humans have a lot of room for mistakes. They're really good. They basically get a 100% success rate. This is what we're seeing here. Overall, all the learning systems are improving. This signal is actually really robust. The best system is the simplest one. It's the binary with filtered fine-tuning. It's this blue line, which we continue for another 3 rounds. Interaction success rate increases by about 50% absolute improvement. So it's a really significant improvement over time. What this signal is measuring is the human adaptation, again, something that Elaine touched on in her talk. So we take the original system and we concurrently deploy it in the last round here, just to see like how much of it is coming because human adapted to the system. It's really negligible in our case. It basically remains in the lower 30s for interaction success rate. Filtered fine-tuning works best. KTO is the only one that struggles, especially in the case of like the binary signal. And this is potentially because the KTO is more sensitive to repeated optimization, something that comes from iterating over rounds again and again. So, it's an open problem to solve that. Overall, all these approaches kind of like are equal. These differences are not the most significant. This is just a really good signal. Turn-level success rate, this is what we're seeing here, also improves dramatically. I'm only showing it for a binary FFT because this requires additional annotation effort. So it goes by an improvement of about over 20% absolute improvement. Another nice thing we see is that the models, even when they're making mistakes, so this is kind of like visual similarity between what the model is doing and what the human are doing. And you can see here when the model is right and when the model is when the model is right given our annotation and when the model is wrong, you see that the model is actually doing similar judgments, more increasingly visually similar judgments to human behavior, even when they're failing. So they're getting closer to the kind of like abstractions and visual reasoning that the humans are doing. And there is a lot more analysis in the paper itself. Okay, so this concludes the first part. I can continue to the second one and take questions at the end, or take questions now? Continue to the end? Okay, so continue to the end, and then we'll do questions. So the second part is about in-context reinforcement learning. It's very different. So if before we were all about fine-tuning parameters, now no parameters are harmed in the process. It's all going to happen in context. So the kind of like the gist of this is basically trying to characterize, if you kind of like think about learning in LLMs, we have in-context and fine-tuning access, and we have the supervised and RL access. We are kind of like interested in what's happening here. What happens when you are doing in-context learning, but instead of assuming access to supervised examples, pairs of inputs and annotated outputs, what happens if you just get the model outputs, let the model guess, and give it rewards? Okay? Okay, so why should we care about this? So first of all, I think it's interesting to characterize the behaviors of in-context behaviors that we are seeing. This is becoming really important in how we think about reasoning models and models that are trying different things and putting them on context. We're relying a lot on in-context learning, even if we're talking about higher level behaviors like more agentive stuff. It also gives you an avenue to quickly modify behavior without parameter updates, and it's kind of like has all these nice properties of online, interactive, and continual learning systems. It also relates to this kind of like notion of relating ad hoc conventions. You can really think about ad hoc convention as a form of RL. So this talk today is focusing on the more restricted case of contextual bandit. This has been studied in the literature a bit, largely with negative results. So Krishnamurti al, this paper kind of like a few months before us, they studied the more restrictive case of multi-armed bandits, so no context, and they came up with a negative result. Largely, the models can't do that. They were able to cook up some prompt to get a multi-armed bandit solution, but their prompt wasn't general, and it definitely wouldn't allow for any context. This paper that came up basically a day after we posted on arXiv, it does something really interesting, takes a very different approach in order to kind of like to fix the conclusions from here. So this is a paper from folks in Google, and they fine-tuned large language models to show contextual bandit behavior. But they did it not in a way that like the models can independently show contextual bandits. They kind of like added crutches. So the models, there is this kind of like very interesting hybrid approach between an algorithm and in-context behavior. There is something that collects statistics explicitly on the side, and then gives it back to the model to run the algorithm that is kind of like amortized into the parameters for fine-tuning. It's a really cool paper. Our findings are a bit different from those and slightly more nuanced. We also take a slightly different approach. Both of these papers look at like very traditional bandit problems. We looked at problems that have a much more important, a big component of natural language. Okay, so what does RL need? So an RL needs, so a reinforcement learning, you need an MDP, a policy, a way to tune the policy, given some kind of like episodes with reward and an exploration procedure. So what does it mean on context? The MDP stays exactly the same. The episode is a tuple of input, output, and reward. The policy is just an LLM that is prompted with the past episodes. And the way to improve the policy is you just add more episodes to the prompt with the reward. It's very straightforward. And then the exploration, well, in the simplest naive case, you just do exploration because you're sampling from the model as you're generating tokens. So it's kind of like, in the simplest case, and we're going to show a slightly more complex one, this is what's going to give you the exploration. Okay, how are we going to do this? Our experimental setup, we're going to follow up a very common setup in the bandit literature, and we're going to use classification problems. So we take this classification problem and we're going to assign the bandit arms are just the labels. That means we have, in some cases, a kind of like quite a large number of arms, 77 for the banking 77 task, 150, and in some cases in track significantly fewer arms. Then we have our inputs. In this, it's like depends on the different classification tasks, and our outputs are just going to be in most of the experiments I'm going to show, they're just going to be the labels. And this is important. These labels are very heavy on semantics. Decline transfer tells you something about what is semantic is there, and you can rely, and that can really help the language model because the model is so good at proficient at reasoning about semantic knowledge. But we're also going to experiment with abstract labels where we replace these semantically rich strings with just kind of like label 1, label 2, label 3. So kind of like completely informationless. And it's going to do interesting things to the learning. Okay, so how does the naive version looks? Well, you prompt with an instructions and concatenate past episodes. You receive textual reward after each prediction, and then you take that new episode and you add it to the prompt. So in step 1, you get the prompt, the query, you want to kind of like decode the output. So it's an intent in this case. So it's declined, for example. Then you take this, you get some reward, and you just add it to the context. And you're going to continue doing this. And slowly your context is going to grow. It's going to have all this like bandit signal on top of it. So here we got it. This is a positive reward. This is a negative reward, and so forth. Okay? So how well it's going to do? Well, actually not so well. So these are the graphs that I'm going to use throughout. So let me explain them in a second. We have two models here. We have Quen 2.5 and Llama 3.1, 7B and 8B. We have a zero-shot baseline. This is this line. This is just what the model does without kind of like any examples. And then we have an upper bound. An upper bound is when we take all the examples in the data. So we're going to do many shot ICL and going to put them on the prompt with gold standard labels. So these are the kind of like the blue dashed line here at the top. And we have banking, clinic, and the three other scenarios. So the naive ICRLs I just saw, this is like the solid line here. It actually performs pretty bad. There is maybe some improvement over zero shot. In some cases, it even gets worse. But overall, we are not really seeing the trends of like improving over time as you're observing more and more reward. Okay? Now, there are two key differences from in-context learning. And in-context learning works great. We have this upper bound here for many shot. One of them is that in context learning, you only get like a kind of like gold standard example. Here in naive ICRL, you get positive and negative episodes. So episodes with positive rewards and episodes with negative rewards. And you also need some kind of exploration. Very important in reinforcement learning, especially early on. So it raises the question of like, what if we try to get slightly closer to in-context learning? So we're still going to let the model guess the outputs and give it rewards. So there's no supervised labels here. But we are going to drop everything that is negative. We're going to keep what is positive. And that's going to make our context look like ICL, even if it doesn't come from some kind of like a gold standard data set. So how does it look like? It's very simple. It follows the same thing. So here we got a positive reward, we add it to the context. Here we got a negative reward, we just drop it. And we continue. So the next one, we'll have the same context actually, and we'll continue to the next example. Okay? Okay. So this one actually performs this one shows like significant learning and improvement over time. So now I'm adding this, we call it naive plus ICRL. And this is like the purple line. Across all the benchmarks, it's showing significant learning. In some of them, in all of them, it jumps very early on. In some of them, it continues going up. In others, it's plateauing. But overall, it's doing very well. There is one kind of like important kind of like caveat here. It's actually not that stable. So for some reason, we're not really sure why, but you can see these fluctuations here. Different data sets, you can see them differently. Track is like really particularly terrible, but overall, there are these kind of like sudden drops in performance, which are really unexpected and often recoverable. And I'm going to go back to this kind of like stability in a second, but first of all, it's also one kind of like interesting question about like this naive plus that does show this learning behavior is like what kind of scaling behaviors we got out of it. So this is the Quen family models. Quen is very nice because it gives you this kind of like menu of scales. So it's expected you see kind of like the expected scaling behavior, right? Models as they you kind of like increase the scale from dark to light in the colors, you see performance going up. You also see kind of like, and again, we're going to go back to this in a second, that stability is increasing, right? You can really see the difference between the smaller models and how they perform here. Although they are improving from zero shot, they're extremely unstable. Whereas the big models, the 72B is actually really stable. It can give you a very kind of like smooth curve. Okay, so going back, so let's kind of like revisit exploration in order to think slightly a bit better about this stability problem. So stochastic ICRL is another version where, so remember, but in the naive version, the way we did exploration is we just sampled from the distribution each token. There's no any external mechanism for exploration there. In stochastic ICRL, we're introducing an external mechanism that dramatically increases the exploration. So how do we do this? At each step, we are going to randomly sample from the past episodes in order to decide which episodes go on the context. So now we're only going to include a subset of the episode in the context. It means that the context is dramatically different each time we are rolling out a solution, right? There is a price to that. Now everything that if we thought before about we can do a lot of KV caching, so we can reuse a lot of computation. Now because we are resampling the entire context, we basically have to recompute the entire KV cache for every episode. It's very expensive, but with enough credit and compute, it's possible. So basically, what we have is kind of like this thing, like we're going to dramatically increase test time compute, and we're going to see what it's going to do to our to the model behavior. Okay, so how does it look? So now we have an episode storage in addition to the prompt itself. When we for every episode after we get a reward, we add it to the episode storage. Whenever we get a new episode, we decide how the prompt looks by flipping a coin or throwing a die for every episode in the storage and deciding what to add. So for example, when here we have a single episode, we decide not to add it. So actually we are continuing in the zero shot for the next episode. As we continue, we have more examples. Maybe we add this one, but we discard this one and so forth. Okay? Okay. So now this adds this green line. So stochastic is much more robust for fluctuations. In some cases, it performs roughly the same or even slightly worse. In other cases, it performs a bit better. So it's kind of equivalent to naive, but it gives you much more stability over time. So now we don't really see these fluctuations. And you can kind of like see this in a clearer way in this kind of like in its kind of like stability frontier. So these graphs, they kind of like chart model size on the Quen family over 2 datasets, banking and clinique. And here we have the Spearman correlation between the ranking of between the ordering of more episodes coming in and the performance. If they are highly correlated, you want to see performance kind of like in a stable way increasing over time. So this will give you a higher correlation. And what you can see is like really this naive ICRL has all this fluctuation. So the stability correlation, stability measure is not that great. Whereas when you kind of like do just naive plus, just keeping the positive episode, you get more stable. Performance is increasing more kind of like more consistently over time, but still not great. Whereas stochastic gives you this like very nice clean frontier here at the top. Okay, so the last thing I promised in the beginning is what happens when we abstract away the labels. So remember, we have these labels. They're very semantics. Semantics helps a lot to models. What happens when we just replace them with kind of like nonsensical strings? Just label 1, label 2, label 3. So this is this kind of like the orange line here. And you can compare it to naive plus as the blue line. So this is abstract versus semantic. And what you can see here is that in general, we are seeing a significant drop in performance, but you still see a significant learning curve. So the model, the effect of the learning is less effective, but it's still happening over time, even though now the labels are nonsensical. And you can fix a lot of it by just adding some exemplars. So, exemplar is like one ICL example for each possible label. So that's going to give you kind of like these lines here that are almost matching in some cases, they are matching the semantic labels. Okay, so I'll conclude with just kind of like papers and credits. So the first paper is retrospective learning from interactions. The lead author is my PhD student, Zoe. And the second paper is LLMs are in-context bandit reinforcement learnings. And the lead author is Giovanni, both of them with a great set of collaborators. So to summarize, in the first part, we saw that learning from implicit conversational signals. What we see that implicit signals are really easy for LLMs to decode, even despite task performance. And then you can learn from them pretty robustly, kind of like without really, with various learning algorithms. In the second part, we looked at like in-context reinforcement learning, and we saw some level of bandit in-context RL, and you can increase stability with more test time compute. I'm happy to take questions, and that's it. Thank you all.
All right, thank you, Yaov, for the great presentation. So same as last time, if you have a question, please, if you can, step out to the mic, and then if you are kind of in the middle, I will give the mic to you. We can take 1 or 2 questions here. Yes, please.
So I have a question about the second paper. What do you perceive as the relationship between sort of the in-context reinforcement learning and just ordinary in-context learning? Like, it seems like it somewhat resembles just giving sort of just like the regular regime of in-context learning, right? I wonder if you how do you perceive the sort of relationship between the two methods?
So I think they're very close to each other, especially the naive plus version. The point is like you generate the labels from the model itself, and if you make it look like regular ICL examples, that's when actually things start to work really well. So in that sense, you want to kind of like make it look like it in order to get it to work really well. However, it's important to understand that the source of the labels is different. Nobody annotated them. So now what you can think of is basically what's going to happen here. If my model has some external force or internally the ability to explore well, then it has the ability to do in-context learning well, then we're going to see nice ICRL. But it still leaves this kind of very unsatisfying. It's a very unsatisfying answer because we're not really taking into account the negative episodes very well. So that's left to be kind of like, that's an open problem. The Google paper that I mentioned initially, that they do the fine tuning, you can think about, you can kind of like consider how you reconcile these approaches, because the way they're training is that they're really showing a much more robust behavior. But it's not an emergent behavior from just existing LLMs. This is something you really have to train very, very heavily for.
A related question. So, what if the model cannot, like your assumption is that the model is able to do well at some examples, and then you're going to put those examples in the context. When it starts like, and we are talking about this banking 77. I'm aware of this data. Aristides, who just asked question, he worked on these data sets. So the number of labels are really a lot of labels. Like banking 77 has 77 labels. These are
77 for banking.
Yeah.
150 for clinic. Yeah.
Really. So in our observation is that like for many of these, even if you say these are all the labels, give this input, what's the output? And most of the times it would predict incorrectly, right? When it starts. So do you have to bootstrap this with the in-context learning and then apply in-context RL?
So our results showed not really, right? Like as long as the model is exploring enough, it's kind of like it will change the variation. The minute it will grab, if it explores good enough, it will start getting some positive results, some positive rewards very early on. Then those are going to look to the model in the next call, just like in context learning examples, and then it's kind of like can build from there. but it has to explore. So I don't have results here, but in the appendix of the paper, we have results with the 5 models, and there the results are much worse. So it really depends on on some qualities of the LLM. Not every LLM can do it, and some of them are better than others. And there is also the kind of like very clear scaling behavior, both for stability and for performance.
Seems to me like this has also relations to some kind of curriculum learning, where you start incrementally.
What?
Curriculum learning.
Yeah, so it does. So you know, Bandit forms curriculum learning. There is no kind of like, well, there's no curriculum that is kind of engineered to follow kind of like any standard. You could kind of like ask yourself how to choose example to show it and maybe speed up learning or make it more robust. I think that's something that is very possible. There's no curriculum in the sense, I mean, the examples are like any Bandit process. They're building on top of each other as you kind of like accumulate statistics, in this case on the context. We didn't engineer or play with kind of like any difficulty scaffolding in a sense, but it's a great idea. I think, you know.
I have a question actually related to the first part of your talk, Yaov. So I really like this notion of having the model decode feedback into some sort of learning signal. I want to ask for your opinions. So when we have the situation where we operate in a somewhat long horizon setting and the feedback is no longer very aligned with a specific action or a turn, how do you see this type of approach working in that setting, and what are some challenges and potential solutions in the long-term setting?
So that's going to be challenging, but I think it's going to be possible. So this kind of feedback, the nice thing about it, so when we are decoding feedback, we're doing it in a very simple way, like at the turn level, right? Even for us, by the way, some of these actions, you flip multiple targets at the same time, and then some of them are correct, some of them are incorrect. And when we assign the feedback, it's going to create some noise. So we already see this to some degree. You can kind of like, I think you will be able to elicit feedback that can be associated with like more subparts of the actions, or like more kind of like atomic parts of the action. We didn't try this, but this is because what you're trying to decode the feedback from is a very rich signal. It's kind of like a whole utterance. So the information is there. Like, you just have to kind of like figure out how to extract it and then how to attribute it to like a subspan of tokens and not just the entire utterance. We just took a simpler approach in this case.
But do you think we'll need some new types of learning algorithms to do that, or do you think the standard kind of, I think right now, filtered imitation learning and learning from demonstration is surprisingly strong. But do you think this will continue to be the case when we extend to the kind of the long horizon setting?
It's probably a scale kind of like consideration, right? If I have data at scale and I can get as much data as I want, then the simple approach will work better. But if you have less data, it's very expensive to get it, then you basically, the attribution is going to help you do much better. But so it all depends. When you just kind of like can automate everything, verifiers and just math and everything is just automated, then just get more GPUs and run it for longer, get million examples. It seems to work well.
All right. Let's give another round of applause for Yaov.